So as we continue with this topic, we want to define a new term, the term that we call enthalpy. So by definition, enthalpy is just a state function. That is, it does not depend on a path. It depends only on the initial state and final state of the system. So it is the sum of the internal energy of the system plus the product of its pressure and volume. Actually, it is equal to the heat change. It is equal to the heat change when a reaction occurs at constant pressure. So when you are thinking about enthalpy, you are carrying out a reaction in a constant pressure container or calorimeter. Now, reactions can absorb energy, and those reactions are called endothermic. And reactions can release energy or can release heat at this constant pressure, and these reactions are known as exothermic. So for endothermic reactions, where the reactions absorb energy, the enthalpy, which has a symbol delta H, is positive. For a reaction that releases energy, delta H, which is the enthalpy, is negative. So we see what sort of reactions are we talking about. So for example, the formation of glucose from carbon dioxide and water, it is called a combustion. So a combustion reaction where carbon dioxide, well, not a combustion reaction as such, but the formation of glucose from carbon dioxide and water is the opposite of combustion, of course. Absorbs energy. You need energy to form glucose. Where do we get that energy? We get the energy from sunlight. So this type of reaction, because it absorbs energy, has delta H positive. In this case, is plus 2802 kilojoules. So we can show this two ways. We can write the reaction equation itself, and then at the end of the equation, we say delta H is equal to plus 2820 kilojoules. Or we can incorporate the delta H within the equation itself. We can incorporate energy within the equation. For the endothermic reactions, energy is part of the reactant. So you can see that energy is on the reactant side of the equation. So if you show me a chemical equation with energy on the reactant side, I will know that this reaction is endothermic. While the combustion, the destruction of glucose to form carbon dioxide and water. Now this is a combustion reaction. This reaction releases energy, and therefore its delta H is negative. Now the other way of writing this equation is to put the energy on the product side. If you put energy on the product side, I will know that this reaction is exothermic. So you can see the difference. Energy on the reactant side, the reaction is endothermic. Energy on the product side, the reaction is exothermic. It just shows that the reaction is releasing energy. Therefore, energy is a product. Now we use reaction profiles to indicate if a reaction is endothermic or exothermic. So actually, I'll be requiring you to draw profiles like these shown on this slide. So for your reaction profile, you need to know all the parts of the reaction profile. The y-axis is potential energy. The x-axis is reaction coordinate or reaction progress. So you need to be able to identify those. Now, for exothermic reaction, the reactants will be at higher potential energy and the products will be at lower potential energy. So you need to show that the reactants are at higher potential energy and the products at lower potential energy. Now, we have each reaction has energy that helps it or that initiates the reaction. That energy is known as activation energy. So when drawing reaction profiles, always show the activation energy. It is this bump here. It's the activation energy. So if you are drawing an exothermic reaction, you are going to start here and you go over this bump and then it goes down below the reactants to get to the product. So I want you to identify this bump and to show me the activation energy. Activation energy always, the line for activation energy starts from the reactant side to the top. So that is activation energy. Start from the reactant line. So this is reactant line to the top. For an endothermic reaction, we see that the potential energy of products are lower than the potential energy of reactants. We see the reactants are at higher potential energy than the products. As usual, the activation energy always starts from the reactant side. So here we see it is starting from the reactant side here to the top. That's where the activation energy starts from. So don't be misled. Do not start activation energy from here to the top. Because you can be misled, say, oh, the activation energy should not be as big as the one we are showing there. But activation energy must start from reactant side all the time. Now, also on this reaction profile, you show enthalpy change. Enthalpy change is just the difference in energy between the products and the reactants. That's all, without including the activation energy. So for here, the enthalpy energy should be from this part to this part. So this distance here is the delta H, change in enthalpy. So it's from the product to the reactant. The same case here, the enthalpy change is between this, from the product to the reactant, delta H. So these are the reaction profiles you need to be able to draw. You need to be able to identify the potential energy, the reaction coordinate, the activation energy for both exothermic and endothermic reaction. And you need to show exothermic reaction, where is the product line, endothermic reaction, where is the product line? Now, we can also talk about exothermic and endothermic reactions based on breaking and formation of chemical bond. If you want to break something, you need to put energy in there. So what we are saying is, if you are breaking chemical bond, the reaction becomes endothermic because you need to put in energy to break the chemical bonds. So as you can see, the two reactions here involve breaking of chemical bonds. Breaking from Cl2 to form Cl and Cl. So that involves addition of energy, and therefore the reactions are endothermic. Formation of chemical bonds involve release of energy. Therefore, the reactions are exothermic. Here you have iodine plus iodine to form a chemical bond I, which is like I2. That reaction releases energy and therefore it is exothermic. Breaking of chemical bonds, endothermic. Formation of chemical bonds, exothermic. Also, we should be able to recognize some processes and say, is this process exothermic or endothermic? For example, if you evaporate water, to evaporate water, you need to add energy. Therefore, the process will be endothermic because you are absorbing energy. Freezing of water is cooling down, so it is losing energy, which means the process itself is exothermic. Wood burning, this is combustion. Combustions are mostly exothermic. A combustion reaction, if I give you a combustion reaction, your first thought is this reaction is exothermic. So things to do with burning are exothermic reactions. Sweat evaporating from your skin and cooling it. I mean, if you want sweat to evaporate, it is the same as evaporation of water. So this is endothermic. So be able to recognize these types of processes as exothermic or endothermic. Now, let's focus on the math of actually what we are discussing about math on enthalpy of these reactions. So by definition, the enthalpy of a reaction, when you have a chemical reaction and that reaction is releasing heat, so the amount of heat released when reactants are converted to products in the molar amounts represented by coefficients of the balanced equation is known as enthalpy of reaction. So we have this reaction here. 3 hydrogen molecules react with 1 nitrogen molecule to make 2 ammonia molecules. So the enthalpy of reaction is negative 92.2 kilojoules. The negative itself, it just shows that the reaction is exothermic. So we can have conversion factors based on this reaction. We know that 3 moles of hydrogen, at least from here, 3 moles of hydrogen will produce negative 92.2 kilojoules of energy. So that is from this reaction. 3 moles of hydrogen produces negative 92.2 kilojoules of energy. 1 mole of nitrogen produces the same, negative 92.2 kilojoules of energy. So anything within this reaction produces this same amount of energy. 2 moles of ammonia produces the same amount of energy. So all these are conversion factors that we can use to determine each specific species in this reaction. Let's look at a problem that will help us understand more about this enthalpy of a reaction. In a Haber process, that is the process they use for making ammonia, 5,800 grams of hydrogen gas was used. Calculate the heat associated with complete reaction of hydrogen to make ammonia as shown by the equation below. So to solve this, we need to come up with the conversion factor. What is our conversion factor? In this case, our conversion factor is 3 mole of hydrogen gives us 92.2 kilojoules of energy. That's what we know. That is our conversion factor. 3 moles of hydrogen produce negative 92.2 kilojoules of energy. So the question is, do we know how many moles of hydrogen we have? The answer is we don't know yet. But we can obtain moles of hydrogen from 5,800 grams of hydrogen. That's what we can do. So to obtain moles of hydrogen, you just need to change the mass of hydrogen to give you the moles of hydrogen. So what we are saying is the molar mass of hydrogen is 2.016 grams. So which means our conversion is 1 mole of hydrogen is equal to 2.016 grams of hydrogen. So that's what we are going to use. So our given quantity in this case, we are converting mass of hydrogen to moles of hydrogen, is 5,800 grams hydrogen times, so we are using this conversion factor, grams hydrogen, then moles hydrogen. Now, which is in this case 2.016 gram, 1 mole. So that gives us the moles of hydrogen. Now we can just add another conversion factor after finding the moles of hydrogen, times. Now it is this conversion factor. We know we are going to have more hydrogen and then kilojoules up here because you want the moles to cancel each other. So to get the moles here from this conversion factor, we have 3 down here, negative 92.2 up there. So from there, we get our answer as negative 88420. kilojoules, which is equal to, that is to two significant figures, 0.88 times 10 to the power 4 kilojoules. So that's how we are able to obtain the amount of energy for a chemical reaction if you are given mass. What you do is you change the mass to moles, then from moles to energy, because you have conversion factors for that. You have a conversion factor for changing mass to mole, and then you have a conversion factor for changing moles to energy. So let's look at this other problem. So for this one, I want you to be able to calculate it on your own, just using the information below, but I can set it up for you. So calculate the heat associated with complete reaction of ammonia, NH3, which is here. Here you are given the molar mass of ammonia, 17.03 gram. This reacts with oxygen as shown by the equation below. And this is the energy. Delta H of this reaction is negative 906 kilojoules. So as usual, first determine the conversion factors. So the first conversion factor tells you that 4 mole of ammonia is equal to negative 906 kilojoules. So that is conversion factor 1. Conversion factor 2, you are given the mass here. You need to change the mass of ammonia to moles. So we can say 1 mole ammonia is equal to the molar mass of ammonia, 17.03 grams. So based on that, based on these two conversion factors, 155 grams is our given quantity. So I will start 155 grams ammonia times, it means down here I put grams ammonia, and I look at my conversion. Which conversion has grams ammonia? It is this one. So it means up here I put more ammonia. Then I go on. Down here I put more ammonia. It means up here I put kilojoules. Then I'll just put the values here. 4906, and you solve your problem. So provide the answer for this problem. All right. Now let's look at what we call calorimetry. Usually calorimetry is just a process that we use to measure the heats of a reaction. And we are going to use this in our lab. Usually we use a styrofoam cup calorimeter, where you have your styrofoam and then you mix two liquids, or you mix a solid and a liquid and capture the heat by observing the change in temperature. So you are able to see how much heat is released or how much heat is absorbed. So we call this a constant pressure calorimeter because we usually do this at constant pressure. So in a situation like this, you dissolve a solid or you dissolve two liquids together, we have a solution. So if I mix two liquids or I mix a solid and a liquid, a chemical reaction occurs. When the reaction releases heat, the solution gains heat. That's what happened. So if you put two reactants in a container and the reactants are reacting, if that reaction is releasing heat or if the reaction is exothermic, then the solution is going to gain heat. Which means if you hold the container containing that solution, the container will feel warm, showing that the solution is gaining heat. An exothermic reaction will warm up a container. But if the reaction is absorbing heat, then the solution loses heat. Which means if you hold, so I'll say when the reaction absorbs heat, solution loses heat. Which means if you hold the container will be cold. So because of that, let me say the heat of solution will be equal to the negative heat of reaction. And if we use the heat equation, the heat of solution will be given by the mass of solution times specific heat capacity of solution times the change in temperature of solution. So we will see how important this equation is and how we use it in our calculation of constant pressure calorimetry problems. So keep this equation. Let's go on and solve a problem. Here we have 0.158 grams metal is combined with enough HCl to make 100 milliliters of a solution in a coffee calorimeter. The temperature of the solution rises from 25.6 degrees Celsius to 32.8 degrees Celsius as a result of the reaction. So if you see the temperature of the solution rising, it means that reaction is exothermic. Find delta H of this reaction. Important information, use density, 1 gram per mil. Why should we use density? Because here you are given milliliters, you are not given mass. So you have to change the volume to mass using the density conversion factor. Here you also given the specific heat capacity of the solution, which is 4.18 joules per gram per degrees Celsius. And you have the molar mass of magnesium as 24.31 grams. So to solve this problem, the first thing you need to do is find the mass of solution. So mass of solution is given by density times volume, which is 1.00 gram per mil times 100 milliliters, which is 100 grams. So we have the mass of solution as 100 grams. Now, the heat of solution is given by mass of solution, specific heat capacity of solution, change in temperature of solution, which in this case we have 100 grams of solution times 4.18 joules gram degrees Celsius of the solution times the change in temperature. So the temperature changed from 25.6 to 32.8, which means our TF is 32.8 minus our T initial 25.6, which gives us 3009.6 joules. So this is the energy of this reaction. But you know what? Once you get the heat of solution, you come back and say, yeah, but heat of solution is equal to negative heat of reaction. This implies that heat of reaction is equal to the negative of whatever you get, 3009.6 joules. So if heat of solution is positive, the heat of reaction is just negative of that positive. So what this tells us is that 0.15 grams of magnesium metal produces energy, which is minus 3009.6 joules. That's what it tells us. Now, but delta H reaction is for more. Delta H reaction is for 1 mole of magnesium, not just 0.158 grams of magnesium. So what you need to do is find the moles of magnesium from 158 grams. So I'll say number of moles magnesium will be given by 0.158 grams magnesium times the conversion factor, which is 1 mole magnesium divided by the molar mass, 24.31 grams magnesium. So this gives us 0.00650 mole. So we have these moles of magnesium. What it means is that 0.00650 mole of magnesium produces this amount of energy. So how much energy will 1 mole of magnesium produce? So for that, you say delta H reaction is equal to negative 3009.6 joule divided by the moles of magnesium that you have calculated, 650 mole. And in the end, we get 463,015 joule per mole, which is don't forget the negative, which is negative 463 kilojoules per mole. This one is the heat of reaction of ammonia, or the heat of reaction of magnesium and HCl to form MgCl and hydrogen. So this is the delta H. So I say delta H reaction is equal to minus 463 kilojoules per mole. So that's how we solve this problem, by using the heat gained by the solution to determine the heat released or absorbed by a chemical reaction. Let us solve a different problem, but similar. In this problem, when 50 milliliters of 0.100 molar silver nitrate is combined with 50 milliliters of 0.100 molar, so I'll put M here for molar, HCl in a coffee couple calorimeter, the temperature changes from 23.4 degrees Celsius to 24.21 degrees Celsius. Calculate delta H for the reaction written as shown down there. Here we are also given density, and we are given the specific heat capacity and the molar mass of silver nitrate. So really, to solve this problem, the first thing we need to do is to know that we are given, here you are given volume here and molarity for this one. The same case, you are given volume here and molarity for that. So the first thing, change the volumes and molarities to give you the number of moles, because number of moles are very important. So I would say number of moles, which has a symbol N, is equal to volume times molarity. So I can say N is equal to M, which is molarity, times V, which is volume. Volume is always in liters. So change the volume to liters. If you are given milliliters, change the volume to liters. So for this problem, the number of moles of silver nitrate is equal to 0.05 liter times the molarity, which is 0.100 mole per liter, which gives us 0.00500 mole. Using the same type of calculation, we see that the number of moles of HCl will also be equal to 0.05 liter times 0.100 mole per liter, which is 0.00500 mole. So we know the number of moles of HCl, we know the number of moles of silver nitrate. And because the number of moles of HCl is equal to the number of moles of silver nitrate in this case, there is no limiting reactant between the two. So to solve this problem, I can select either of them. So we are going to use this one. because there is no limiting reactant. Now, once you determine the number of moles, so I'm gonna get rid of this part so that I have enough space. Once you determine the number of moles that you want to use, then you go back to the solution. Mass of solution. You need to find mass of your solution. So, to get the mass of your solution, you need to add the two volumes. So we have 50 milliliters. So at this point, for obtaining the mass, you need to use milliliters. While for obtaining the moles, you need to use liters. So we have 50 milliliters of silver nitrate plus 50 milliliters of HCl. So this one, if I just so 50 milliliters of AgNO3 plus 50 milliliters of HCl, which gives us 100 milliliters. This one times density, which is 1.00 gram per mil. So we see that our mass is 100 grams. So take note, the mass is obtained from the total volume. Mass is obtained from the total volume. From total volume. Don't just use 50 milliliters. Use 100 milliliters to obtain your mass, because that will be the total volume of the solution. Now, once you obtain the mass, you come back and say Q solution, the heat of solution, is equal to 100 grams, that is the mass of solution, times 4.18 joules grams per degree Celsius times the change in temperature, which in this case is 24, because this is where the change in temperature is. 24.21 minus 23.40 degrees Celsius. Once you do the calculation, you find that we have 338.58 joules. So the heat of solution is 338.58 joules. But we know that the Q solution is equal to negative Q reaction, which means Q reaction is equal to negative 338.58 joule. As such, delta H reaction, you just divide the heat of reaction divided by the number of moles. 338.58 joules divided by 0.005 mole, which gives us negative 67716 joules per mole, or negative 67.8. That is 67.8 kilojoules. Negative 67.8 kilojoules per mole. So that's how we solve this problem. So let us move on to a different type of problem. Hess law. So, for example, you have this equation here. Consider the equation for the formation of ammonia. 3 hydrogen, 1 nitrogen to give us 2 ammonia, and you have energy there, negative 92.2 kilojoules. This reaction actually occurs in 2 steps. So first step, you have hydrogen and nitrogen to form this intermediate. And then the intermediate reacts with another hydrogen to form ammonia. Each of the steps has its own energy. So Hess law says that if the equation can be expressed as the sum of a series of steps, then delta H reaction for the overall equation is the sum of the Hess of reaction for each step. But it's not as simple as it just looks. So let's look at how we can navigate through the math of Hess law to find delta H reaction based on several steps. But before we go on there, we are just going to talk about elements, enthalpy of elements. So enthalpy of elements in their stable state is 0. For example, if I show you an oxygen element, which is O2, this one has an enthalpy of 0. Carbon has an enthalpy of 0. Hydrogen element on its own has an enthalpy of 0. SH, which is also an element, has an enthalpy of 0. So that is important when you are solving enthalpy problems. You will see why it is important. Let's look at this Hess law problem. Consider the reaction carbon solid and water gas to form carbon dioxide and hydrogen gas. What is the enthalpy of this reaction? That's what we want to determine. But we are told that this reaction occurs in 3 steps. The first step is this reaction shown here. The second step is this reaction shown here. And the third step is this reaction shown here. So how do we obtain delta H of reaction for this? So to solve this reaction, I am going to call this one a parent reaction equation, or it is the overall reaction equation. I am going to compare the parent equation to each of the equations that we are given. So let me just show you what we are going to do. So I'll come to this parent equation and select or isolate carbon, just carbon. I am isolating carbon there and say carbon. What is carbon in this reaction? Is it a reactant in the parent equation? The answer is yes, it is a reactant in a parent equation. Then I will go to my 3 equations and find where carbon is. Let me search. Yep, here is carbon. So I have found carbon from my 3 reactions. I ask the same question. Is carbon a reactant in my equation here? The answer is yes, it is a reactant. I ask a question again. In the parent reaction, how many carbons do I have? I just have 1 carbon. What about in my step 1 of a reaction? How many carbons do I have? The answer is I have 1 carbon. So based on that, I am going to conclude that this reaction remains as it is. I'm not going to change this reaction. So this reaction will remain as it is, and the energy of this reaction will just be negative 393.5 kilojoules. There's no need to change. It has 1 carbon, and that one carbon is a reactant. Then I'll go on and search for, let's say, water. Before I go for water, maybe I'll go for carbon monoxide. I go for carbon monoxide. In the parent equation, carbon monoxide is a product. It is not a reactant. So I come back to look at my 3 steps there and see, where is carbon monoxide? There it is. I found it. So the question again, is carbon monoxide a product in this case? The answer is no. Carbon monoxide in my 3 equations is a reactant. But I want to make it a product. I need to make carbon monoxide a product. So what do? I am going to reverse this reaction. So reverse this reaction so that carbon monoxide is a product. Another question is, how many carbon monoxide do I have as a reactant or as a product in my parent equation? How many carbon monoxide do I have in the parent equation? Here I have only 1 carbon monoxide, but here I have 2. So it won't work. For me to have 2, it means I need to multiply this reaction by half or divide the whole reaction by 2. Right. So I'll do 2 things. First, I'll reverse the reaction and then multiply it by half. So if I reverse this reaction, the enthalpy becomes positive. And if which means I am going to have plus 566, then times half. If I reverse the reaction, the enthalpy changes from negative to positive. And if I multiply it by half, the enthalpy divides by 2. So which means what I'm going to have here is plus 283.0 kilojoules. Then I go to the third reaction. That is hydrogen. What is hydrogen in the parent equation? So in the parent equation, hydrogen is a product. Here it is a reactant. It is a reactant here. So I'm going to reverse this reaction also so that hydrogen is a product. Now, how many hydrogens do we have in the reactant in the parent equation here? Here we have only 1 hydrogen, but here we have 2 hydrogens, which means I also need to multiply this by half so that I have the same amount of hydrogen in the parent equation as in this step of the equation. Which means I'm going to have, because I reversed this, it becomes positive 483.6, and I multiply this by half. So in the end, I am going to have let me just check what I am having. I am going to have plus 241.8 kilojoules. So once I do that, I will add these to give me my delta H of reaction, which will be plus 131.3 kilojoules. So here is equal to plus 131.3 kilojoules. So in other words, what you are showing is I'll write this equation as it is: C solid plus O2 gas to give me CO2, and the energy is 393.5 kilojoules. While I reverse this one, I reverse it and divide it by 2. So I will have reversed and divided by 2. I will have CO2 to give me CO plus half oxygen, and the energy is plus 283.0 kilojoules because I reversed it and divided by 2. I do the same thing for the third one, reverse and divide by 2. I am going to have H2O to give me H2 plus half O2. When you multiply by half, you are multiplying the whole equation, not just one thing. So you are kind of doing like this. I'll put in parentheses and multiply by half. So I am multiplying by half the whole equation. So here I have plus 241.8 kilojoules. So if I play around with this equation, these two oxygens will cancel with this oxygen. This carbon dioxide cancels with carbon dioxide here. So in the end, what we remain with is on the reactant side, we have carbon and water. So we have carbon solid plus water gas. On the product side, we have this carbon monoxide and hydrogen. So CO gas plus H2 gas. And the energy for this is 131.3 kilojoules. So we are just going to finish the other Hess law problems in the next short video that I'm going to make. Thank you.